Hello, everyone. So, what I wanted to do was do a quick review for the second Physics 212 lab exam. So, I'll go over some questions that will definitely be very similar to those that are on the exam, and then some of them I will just sort of outline how you would solve them. Okay? So, definitely what you want to do, let's say you have, let's start with projectile motion. Let's say we have an object that's launched at some initial velocity. So let me draw a coordinate system here. Let's say I'll call it V naught. Let's say the magnitude of V naught is 90 meters per second. And let's say the launch angle was 35 degrees. So one thing I could ask you to do, very simply, is find the components of the initial velocity, right? So how do you find the components? Well, you'd have to project this velocity onto the x-axis. You're basically finding the vector components, right? So then this would be v naught x, and if I project it onto the y-axis, this would be v naught y. And then if you extract the right triangle, so that triangle right there, we know this angle is 35 degrees. We know that the hypotenuse is the magnitude of velocity, right? So this is going to be 90, and really it has units of meters per second. And then this is v naught x, and then this side is the same as v naught y, right? So this length is the same as that length, so that's really v naught y. So then, how do we find, let's start with v naught x. Well, v naught x is adjacent to the angle. We know the hypotenuse. So what trig function relates adjacent and a hypotenuse? That's cosine, right? SOHCAHTOA, so ca. So I know that cosine of 35 degrees must be the length of the adjacent side divided by the length of the hypotenuse, which is your v naught, right? Your magnitude of v naught. So that means v naught x is simply going to be v naught times cosine of 35 degrees. So in this case, your v naught is 90. So 90 times cosine of 35. And it's positive, right? It's pointing in the positive direction. So this is going to be positive 73.7 meters per second. And then to find the y component, well, v naught y is opposite the angle. So what trig function involves opposite and hypotenuse? That's sine. So I know that sine of 35 degrees must be v naught y divided by v naught. So v naught y is v naught times sine of 35 degrees. But again, v naught is 90. So plug that into your calculator, make sure that you're in degrees and not radians, and you should get 51.6 meters per second. And again, it's positive, right, because the y component is directed upward, right, because we're in the first quadrant, so both the x and y components are positive. Okay, so something simple like that, right, just find the components of initial velocity vector. Okay, another... so actually, using the same information, let's see if we can find the range of this projectile that was just launched here. So remember, the range, so let's say v naught is the same, right? So v naught is 90. The angle is 35 degrees. And the range is defined to be from the point of projection to a point on the path that's at the same elevation as the point of projection, which means it lands at the same height. So this horizontal distance, it's really a horizontal displacement, is the range. Now, there's a couple ways you could compute the range. You could use your constant acceleration kinematic formulas, right? And using the y information, the fact that delta y is 0, you could find the time it takes. And then using the x information, the fact that the acceleration in the x direction is 0, so the velocity is constant in the x direction, you could calculate the horizontal displacement, which is going to be the range, right? So you would need to do it in 2 steps. However, in lab, we were already given a formula, and you probably also have this in lecture as well, a formula for the range, which is basically derived from kinematic formulas. So it's easier, since we have all the information, just to plug right in. So we know the range is going to be equal to V naught squared times sine of 2 theta divided by g. Well, V naught is the magnitude of the velocity, right? It's the length of that vector. So that's just 90. So it'll be 90 squared times sine of 2 times 35, right? So sine of 70, divided by, and in g, you have to make sure, since we're using SI units, g is 9.8. If it were CGS units, then it would be 980. So you got to be careful on what units that we're in. And if you work this out, you're going to get 776.7 meters. So that would be the range of that projectile, assuming no air resistance. Another question I could ask is I could give you, so I could also give you R. I could give you the range and V naught, let's say the initial launch speed, and ask for theta, right? So I could give you different variables, and using that formula, you could solve for the remaining unknown variable. So I could give you R and V naught and ask for theta, right? So you want to make sure you know how to do that. Like, for instance, if I gave you the velocity was 90 and then the range is 776.7 meters, you should be able to come up with the fact that it's going to be it was launched at 35 degrees, okay? All right. So another example from projectile motion. Let's say that you're told that, first of all, let's say this is the floor, right? And you have an object, a ball, that's dropped from rest. And then you have a ball, starts at the same height, but it's launched horizontally. So it has some velocity in the x direction. So I'll say ball launched horizontally at the same height. So the question is, which ball hit first? Now again, if you remember from lab, we actually did this experiment when we had those blue launchers, right? And we had the slotted ball, the solid steel ball, and the slotted steel ball, the one with the hole in it. And we launched it at the same time. And because, and the key thing is, they're starting at the same height, right? This height is exactly the same. And also, their initial velocity is in the y direction. So v naught y, or v initial y, is 0, right? Both of them are 0 meters per second. And they're both being acted on by gravity. So their motions in the y direction are going to be exactly the same, right? Like when this ball is here, this ball is the same place in the y direction. When this is here, then it's here. So it's going to match in the y. Then when it's here, it's going to get faster and faster, right? So then it's here. When it's here, it's here. So these, I didn't draw this very well, but I'm trying to indicate that these y positions are going to be exactly the same. So it's going to match. The motions are going to be the same in time. Okay, so they should hit exactly the same time, right? Okay, there will definitely be some Newton's second law type problems. So let me do some examples here. Let's say we have two masses on top of one, like two boxes, let's think of, on top of one another. So this is like mass 1, and then maybe mass 2. And they're going to move together, right? Let's say there's an applied force. So I'll call that FA. I'll assume there's friction acting opposing the motion, right? So this is FK, kinetic friction. And then, of course, there's the weight. And when I say weight, I'm going to say the weight of both of these objects. I'll just call it W, but it's the weight of M1 and M2, both of them. And then there's going to be a normal force that the floor exerts on both objects upward. Okay, let's say you're told, let me make a little room here. Let's say you're told that the acceleration of this system of the two objects, let's assume they move together, is 50 meters per second squared. Let's say you're told the magnitude of FA, the applied force, is 300 newtons. And FK, the magnitude, is say 100 newtons. Let's say you're told M1 is 2.5 kilograms. And the question is, find M2. Let's say we don't know M2. Okay, so we're going to use Newton's second law. We need to have a coordinate system. Well, probably we would use a standard coordinate system where x is to the right and y is vertically upward. It turns out because we're given the kinetic frictional force, we don't even need to worry about the y direction, only the x direction. So using Newton's second law in the x direction, I have the sum of the forces in the x direction must equal m. It's really m, it's a total mass, right? M1 plus M2 times AX. Because they're moving together. So if we write this out carefully, I want the x component of the applied force. I want the x component of the normal force. I want the x component of the weight. I want the x component of the kinetic frictional force. That's got to equal M1 plus M2 AX. Well, the x component of the applied force is 300, right? And it's positive. So this is just 300. The x component of normal force is 0, right? None of that vector is in the x direction. Same thing with the weight. And then for the kinetic frictional force, it's going to be negative 100. And that's got to equal, what else do we know? We know M1 is 2.5. I don't know M2, so I'll just leave it as M2. And we know AX is 50 times 50. So now, basically, your only unknown is M2. We can solve this for M2, right? So I have 200 on the left-hand side is equal to 2.5 plus M2 times 50. You could distribute into 50, but it might be easier in this case just to first divide by 50 to get rid of it. So that's gone. So I'm going to have 4, right, is equal to 2.5 plus M2. And now finally I can subtract 2.5 from both sides. So it looks like M2 is going to be 1.5 kilograms. So that would be the mass, the second mass, the mass that's sitting on top of the other one. Right? So together we have, like, you can think of it, ultimately we had a system of like a 4 kilogram mass when you combine them. But we just wanted to find M2. Okay, so something like that. Here's another example. Let's say I have this. Let's say I have a single object now. Let's call it M. And there's several forces acting, so I have an applied force again to the right. I have a kinetic frictional force to the left. I have a weight acting down. We know that's mg. And I have a normal force acting up. Okay, so again, I'm going to leave some room here. Let's say we're told that the mass is 100 kilograms. Fa, the magnitude of that applied force is 500 newtons. Let's say we're told the coefficient of kinetic friction is 0.3. And I want to figure out, first of all, I want to figure out the kinetic frictional force. And then once I have that, I want to answer the question, what is the acceleration in the x direction? Okay, and we'll use the same coordinate system. We'll say x is positive to the right, y is positive vertically. Okay, well, in order to answer this question, what is F of k, right? What is the kinetic frictional force? Remember, the model, the equation for the kinetic frictional force is F sub k equals mu k times n. So I need to know the normal force in order to find Fk. Well, how do I find the normal force? Well, I can apply Newton's second law to the y direction, right? I know the sum of the forces in the y direction is equal to ma(y). So I want the y component of the applied force, I want the y component of the normal force, I want the y component of the weight, I want the y component of the kinetic frictional force, right? Those are all my forces, so I want all the y components. That's got to equal ma(y). Well, the y component of the applied force, it's acting in the positive x direction. There's no y component, right? The normal force is all of n, and it's positive, so I'll just write it as n. The weight is the entire weight but negative, so it's minus mg. And then the y component of the kinetic frictional force is also 0, right? It's all in the negative x, so there's no y component. And then since this object is not moving off of the surface, the acceleration in the y is 0. So this equation tells us that the normal force, if I add mg to both sides, is equal to mg, is equal to the weight. So therefore, I know that Fk now is going to be mu k times the normal force, but we just found that that is mg. So now we can answer our first question, right? I can plug in here. Mu k was 0.3, m was 100, and g is 9.8. And if you evaluate that, you're going to get 294 newtons. So that's Fk. Box that. So that's our first, that's the answer to the first question, right? So Fk is 294 newtons. Now, how do I find Ax, the acceleration of the system? Now I need to do Newton's second law in the x direction. So now I have sum of the forces in the x direction equals max. So now I want the x component of the applied force plus the x component of the normal force plus the x component of the weight plus the x component of the kinetic frictional force. That is equal to max. Well, the x component of the applied force was given as, 500? There is no x component of normal force, right? It's all in the positive y direction, so that's 0. There's no x component of the weight, that's 0. That's all in the negative y direction. And then the x component of the friction it's 294, but remember it's negative, right? Because the direction, I need a sign here, that's important. So it's negative 294. And the mass was 100, and we're looking for Ax. So 500 minus 294 is like 206. That's equal to 100 Ax. And now I can just solve for Ax, divide by 100. So it looks like the acceleration in the x direction is going to be 2.06 meters per second squared. Okay, so again, all we did was apply Newton's second law. In this case, we had to use the y direction first to find a normal force, so that allowed us to compute the kinetic frictional force because we needed to know the normal force there, right, mu k times n. And then to find the acceleration, we had to use the sum of the forces in the x direction, right, apply Newton's second law to the x direction. Okay. Okay, another example is exactly what we did in lab, where we had a cart on the air track. It had a mass M1, right? And then we had the pulley, then the rope, the string went over the pulley, then we had the suspended mass, the hanger. M2, we release it from rest, right? It accelerated to the right. So I could like give you, so given M1 and M2, I think we use CGS units, so let's say I give you in grams. I could say calculate A, the acceleration, and that would be centimeters per second squared, right, if we're in CGS units. Or I could also ask you to calculate T, the tension, and that would be in dynes. So, but this is really straightforward. It's really plug and chug because we derived those formulas, right? Remember, the acceleration was m2g over m1 plus m2. And you just have to be careful. G in this case, if we're in CGS units, would be 980, right? Centimeters per second squared. And in tension, there's a couple ways you could get it. If you know m1 and you know the acceleration, it's m1a. Or if you want to get it using m2, it was, let's say, it was m2, I believe it was g minus a, right? So that you could use either of those equations to find the tension if you're asked to calculate the tension. So either of these would work, or. All right, so yeah, definitely a straightforward question like that will be on there. Friction, I could give you a graph of the force versus time, like what we got from the GLX device. So this is force in newtons. This is time in seconds. And, you know, it rose to, like, remember it peaked somewhere, then you kind of pulled it at a constant velocity, kind of plateaued, and then when you stop pulling, it goes down to zero. So I could ask you to calculate mu s and mu k. And remember, mu s is simply going to be Fs max divided by the normal force, and mu k is going to be Fk divided by the normal force. So I'd have to give you enough information to find the normal force, but in this lab, when it was on the flat surface, the normal force was equal to the weight, right? The weight of the object, of the cart. So then you'd only need to find Fs max and Fk. How do you do that? Well, you could estimate it, right? If you remember this peak right here, this peak is Fs max. And then the plateau, sort of the average of the plateau, is Fk. So if you were to estimate by reading this on the scale here, this value would be like Fs max. And then the average here, that would be Fk. So you could estimate those values, right? And then as long as you have the normal force, you could calculate mu s and mu k. So something like that. Let's see, what else? We definitely spent time talking about work and energy. So let me outline like a problem I could give you in work and energy. Let's say we have this object on a flat surface. Okay, so there's my object. It has a particular mass. We're going to assume no friction. And we're also going to assume it starts at rest. So what are the forces acting? Well, let's say we have certainly the weight acting down. We have a normal force that the surface exerts on the object perpendicular to the surface, right? So that'd be straight up. And then let's say we also have an applied force, so someone's pulling on this, called Fa. And let's say that angle it makes is like 20 degrees. Okay? And then this is going to undergo a displacement to the right of, so this is like delta r. It's really going to be a vector, right? So I'll say this is delta r, vector. That's my displacement. So it's going to end up over here somewhere. I should really make that the end of it, right? Hold on. So something like that. And let's say you're given that delta R is 2 meters. You're given that the applied force, the magnitude of the applied force is 50 newtons. And you're given that the mass of the object is 10 kilograms. Okay, and we want to find several things. So one thing I could ask is, what is the work done? So let's say this is A. What is the work done by the applied force? By that force. Just that force, right? Just Fa. Well, as it undergoes that displacement. So remember the definition for work due to Fa, it's going to be the magnitude of Fa times the displacement times the cosine of the angle that the force vector makes with the displacement vector, which in this case is 20 degrees, right? So to calculate this, it's simply going to be 50, right? That's 50 newtons times 2 meters times cosine of 20 degrees. And that ends up being like 90 around to the nearest tenth, so 94.0 joules. That would be the work done just by Fa. Okay, what about, I could ask you in this example, compute the normal force. What is the normal force? Okay, so here, let's set this up. So I want to compute the normal force. So in order to do that, I need to apply Newton's second law to the y direction, right? But first, I need to find the components of the applied force. Let's do that first. Let's find the components of Fa. So remember Fa, I'll draw a little coordinate system here. We're assuming x is to the right, y is vertical. This is Fa. We know the magnitude of Fa was, what was it, 50 newtons. And I want to find, and I also know this angle is 20 degrees, right? I want to find the x component, so I'll project this onto the x-axis. So this is like Fax, and then I want to find the y component, so I'll project that onto the y-axis. This is like Fay. So if I extract out my right triangle here, this is 20 degrees. The hypotenuse is the magnitude, so that's going to be 50 newtons, right? The magnitude of Fa. And I'm trying to find Fax, and Fay. Well, Fax is adjacent, right? So that's going to involve cosine. So we know that Fax is going to be 50 times cosine of 20 degrees. And that is equal to, so that's equal to 40, or about 47. So 47.0 newtons. And then Fay is going to be 50 times sine of 20 degrees. And that's equal to like 17.1 newtons. And they're both positive. Okay, so now that we have that, let's apply Newton's second law to the y direction. So I have sum of the forces in the y, do it right here, equals MAY. So I want the y component of the normal force plus the y component of the applied force, which we just found, plus the y component of the weight, that's got to equal MAY. Well, how much of the normal force is in the y direction? The entire amount, right? So the NY is just all of N, and it's positive. How much of the applied force is in the y direction? Well, it's going to be actually, here I'll write it out again as it's positive, right, because it's acting upward, and it's FA times sine of 20 degrees, which we know is 17.1, but I'll write it out like that for now. And then how about the weight? How much is in the y direction? All of it but negative, right? So negative mg. And then this object is not leaving the surface at all, so the acceleration in the y direction is 0. So it looks like in this case, right, if I bring these two terms, if I subtract this from both sides, so I need to subtract it from the right-hand side. And if I add mg to both sides, so add mg, then the normal force, it looks like, is going to be mg, I'll write that first, minus the y component of the applied force. So if we plug in here, right, this is 10 times 9.8 minus, and we already calculated this, right, it's 50 times sine of 20, but that was like 17.1 or something. So the normal force is going to be 98 minus 17.1, which is equal to 80.9 newtons. And notice it's not equal to the weight anymore, right? Like in many cases we had just the normal force is equal to the weight. In this case, I have to subtract this additional thing because I have this other force that I'm pulling up with. It's going to lessen what that normal force is because I'm exerting a force up. If this force was going down, then it would make the normal force larger, right, than the weight. Since it's pulling up, it's going to make the normal force less than the weight. If there was no force here, the normal force would just equal the weight. So that's a little bit different than what we normally find, because normally the normal force is just equal to the weight. So you have to be careful. If there's other forces in the y direction, that's not necessarily true. Okay, another question. So now that we have the normal force, what is the work done by the normal force? I'll go to another page here. So this is like question C, I guess. So what is the work done by the normal force? Well, we can use our formula, right? The work done by normal force in general is going to be the magnitude of normal force, we know what that is now, times the displacement, times cosine of the angle between the normal force and the displacement. Now, it turns out we don't even need to plug any of these in, although we just found n, but we don't really need to plug it in. We know delta R is 2 meters. Why don't we need to plug those in? Because the angle between the normal force, if remember was acting straight up, and the displacement was to the right, is 90 degrees. And cosine of 90 is 0. So this, it doesn't even matter what these values are, this is equal to 0. So the whole thing is going to be 0. So the work done by the normal force is 0 joules. If you remember from lab, I said anytime you have a force that's perpendicular to the displacement, it doesn't contribute any work, right? It doesn't cause any work to be done on the system if it's perpendicular to the displacement. Okay, another question you could be asked, what is the final velocity of that object? Let me go back to. So what is the final velocity of the object? So if we go back to, let me go back to the actual object of drawing here. Right, so it's starting at rest. We're applying a force. We also have the normal force and the weight acting on it. It's going to accelerate to the right. Right, we're applying this force for over a distance of 2 meters, so delta r is 2 meters, and we want to know the final velocity when it gets to that position. What is the final velocity? Okay, so to answer that question, we're going to use the work energy theorem, right? We know that the net work done must equal the change in kinetic energy, which is really the final kinetic energy minus the initial kinetic energy. But how do I find the net work done? Well, the net work done is the work done by each of the forces, right? So it's the work done by FA plus the work done by the weight plus the work done by the normal force. However, we already know the work done by FA. We calculated that at the beginning, right? It was 94 joules. What's the work done by the weight vector, the gravitational force? Well, it's perpendicular to the displacement, right? So that's going to be 0. And then we just found that the work done by the normal force is also 0 because it's perpendicular to the displacement. So the net work done is really the work done just by the applied force. So this is going to be 94. So W net is just 94. And then the change in kinetic energy, right, we can write this as the final kinetic energy. Remember, kinetic energy is 1/2 mv squared, so this would be 1/2 mv final squared minus, and then initial is 1/2 mv initial squared. However, the object is started at rest. So the initial velocity is 0. That means the initial kinetic energy is 0. So the net work is simply going to be 1/2 mv final squared. Okay, so let's actually solve for v final now. Okay, so you could just solve this algebraically for v final. So basically, if I multiply both sides by 2, then I'm going to have 2 times the net work is equal to mv final squared. Then I would divide by m, so the m's cancel. And then finally I need to take the square root of both sides. So you're going to end up with v final is the square root of 2 times the net work divided by m. Or if you want, at this point right here, you could just plug in values, right? We know W net is 94, M was, what was M? 10 kilograms, and you could solve for V final. Same thing, right? I just decided to write it out algebraically. So I'm going to plug in at the end here, so now I have 2 times 94 divided by 10, and then take the square root of that. And if you do that, you're going to get 18.8. No, sorry, that's VF squared. You're going to get 4.34. 4.34 meters per second. So that's going to be the final velocity. And again, how did we get that? We got it from the work energy theorem. The fact that the net work done has to equal the change in kinetic energy. Okay, and then there were several questions I asked you that were situations exactly like lab. So basically, if you understand the situation and you know where to find the formulas, of course it's open book, open notes, so you can just look this up, you'll be able to answer these questions. So let me just outline these. I'm not going to go through any with particular values. I'm just going to outline them. So I'll say situations similar to lab. So for instance, you could have a situation where we have the wooden ramp. It was at some angle, respect to horizontal, and then we had the cart. Remember the cart on the wooden ramp? Its mass was m1. Then we had a pulley here, and then the string went over the pulley, and then you had the suspended mass, m2. Again, this is like the wooden ramp. And the you adjusted M2 such that this cart moved up the ramp at a constant velocity. And what we did basically in this lab was we calculated the tension in the string, right, which is the same as this tension acting up, two different ways. So I could give you a bunch of information and ask you to compute the tension. So let's say, given information, compute, and we did it two different ways, right? We called one T experimental and then T theoretical. Let's call it T theory. And how do we find T experimental? Well, that dealt with the hanging mass, right? Remember, it was just M2G. It's just the weight. T is equal to the weight. Why is that true? Because if this is moving up at a constant velocity, this is moving down at a constant velocity. So there's no acceleration. So the tension acting up, that force acting up, must equal the force acting down, which is the weight. And then the other way that we computed it, T theory, was involving all the information from this cart, right? Where we had the weight, we had the normal force, we had the frictional force. And remember that equation, T theory, double check me on this, but I'm just doing this from memory. I think it's M1, it was M1G, right, times mu K cosine theta plus sine theta. So I'd have to give you the masses, I'd have to give you theta. So given all information, you should be able to compute T experimental, T theory. Okay, let's see. Another experiment that we did in lab was the ballistic pendulum, right? This is like the last experiment. So again, if we look at what's going on before the collision, so here's the pendulum, here's the ball moving at some initial velocity. So this is like before collision, and then I'll draw a dashed line here. After the collision, so this is before, this is after. And now basically the ball was embedded in the pendulum. It moved off at some velocity, v, and then it swung to like a maximum height here. And that height was like from here to here, right? So that's like our delta H, from there to there. So I could ask you to compute a bunch of things, right? I could say compute delta H, and there was a formula for that. Compute this velocity of the ball pendulum system right after the collision, right, the capital V, and then ultimately you work back to compute the velocity of the ball before it collides, right, V naught. Okay, and again, if you understood the lab, then you're going to have no problems with these. These are just formulas that we use in the lab itself. And then one more that I will definitely ask is involving the work energy theorem, where we had the ramp with the Pasco car. It was at some angle. And here it was moving at some velocity. And we could calculate that because we had a photo gate. Right, so we had like the photo gate. I don't know how to draw that. Let me do it in red here. So there was like a photo gate here. So you could calculate the initial velocity, and you could also find, I'd have to give you like the height, right, the initial height. And then it traveled up the ramp, and then at some point, it was at the highest point where it had zero velocity, but it had some final height. So what I could ask you to calculate is the mechanical energy at this first position, so call this like position 1, and at the second position, position 2. So I could ask you to calculate mechanical energy at position 1 and position 2. And remember, the mechanical energy is simply, because there's no friction involved here, it's simply the sum of the kinetic energy, so K, or sometimes I write it as KE, plus the gravitational potential energy, which I'm just going to write as PE right now. So it's the sum of the kinetic energy and the potential energy at each of those locations. And at this highest point, remember, it's at rest just for an instant. Okay, and we know that mechanical energy should be conserved, right? So if I calculate it actually at any point in here, even if I calculate it here at the initial and final, or even the middle, the sum of these two should give you the same value, right? The ME should be the same, should be conserved at all locations on there. All right, and so that should give you a really good idea of what types of problems to expect on this second lab exam. Great, thanks.